Hi, and welcome everyone to my first video. So this video, I will explain my first self-learned algorithm. It's named Mamba linear time sequence modeling with selective state spaces. Okay, so in order to understand the Mamba or algorithm, we need to surpass these five outlines. First of all, we're gonna be asking the question, what is the long context bottleneck in transformers? Because this question will be the premise to develop the Mamba algorithm. So basically, I will introduce a little bit. So before we have a transformers, most of the sequence task is gonna be depend heavily on RNN, OSDM, GRUs, or even sequence to sequence. And however, is plays two major issues. The first is vanishing gradients, which mean like the previous context will be forgotten by the time. And the next one is gonna be limited in parallel, which means it cannot process parallel in the GPUs, and this is one of the biggest bottleneck. And transformers propose to solve both the major problem by scaled up product attentions to remove the recurrency, which is solved for the vanishing gradients. And the next one is multi-head attentions, which solve for parallel. And here is the high-level architectures of transformer models. So as first, the transformer models is proposed to solve the problem for Google translations. And after this, it's gonna be play a really foundational platform and the background for the current generative AIs. So here is the architectures. So basically, it's going to be surpassing to the encoders and decoders, which is on the left and on the right, respectively. So the encoders will receive the request and create the key and value. Meanwhile, the decoder will respond the request to to have the kill. Next, we're gonna be investigate about the scale dot product attentions. So here is the main mechanism of transformers. So it's have a three vectors. The first is Q. So Q is the query, which means the question for the decoder is going to be asking itself to provide a response. Meanwhile, the key and value is the token label descriptions, and the value is the actual contents of each token contribute to the output. And here is the visualizations, what is transformers from IBM to create the Q, key, and value. And here is the math formulas for attention. So it's going to be used the dot product operators to calculate the query and key. So the T is here is the transpose metric, and D here is used for scaling. And meanwhile, the V is the value. And the softmax is the activate functions that range from 0 and 1 and is going to be using to create the weight for the value. The next one is multi-head attention mechanism. So instead from the original, let's say we have the 512 dimensional space, we're gonna be processed is only in one head. But right now, the transformers will split it attention into 8 head. So 8 head is going to be parallel to calculate on the GPUs, and at the end is going to be concatenate in each other's. That's why it can solve the parallel problem. However, although the transformers have these advantages, but it has to face one of the biggest long context bottleneck, that is the quadratic scaling in memory and computations. So here is the image of visualization. And here is we have the attention formulas, which is Q and key. So basically here we gonna be having the visualization, let's say for the metric with 80 and 16. And when is calculated attention score, we need to transpose the metric into the 16 and 18. So we're gonna be have the result for 18 and 18 here. So basically, it's gonna be scaled up to L powers of 2. So the more we're gonna be increase the key and Q value, that mean like it's gonna be having the quadratic in scaling, one of the biggest disadvantages of transformers. Now let's move to the next part, the foundations of Mamba. So what is actually Mamba? So the Mamba is going to be overcome the bottleneck for quadratic complexity, which is appears on transformers, and is used the new ideas, which is came from control theory, from the mathematical equations, and this architectures is independent from the transformers RNN and CNN, which basically is not depending on their innovations. And the Mamba will achieve the robust performance in both latency and memories. So we have the O of L in computing and O of 1 in just compress the memory state. So it's going to be proposed two mechanism. The first is the selective mechanism. What does it mean? Is called selective because it's allowing the mechanism in order to selectively remembers or forget informations which is no more important or really important based on the input. And the next one is hardware aware selective parallel scan. So that means like in order to run the selective mechanism, it needs to be hardware aware about the GPUs. And in order to do it, is have to have the algorithm in order to running on the GPUs. And here's is the Mamba block architectures. Basically, it's going to be stacking many block in each others. And here's is the image that I referenced from IBM. The first, we're going to be input, and we are going to be projections into two branches like this. The main brain will surpass through the selective mechanism, and the second one will be passing here and aggregate at the end. After this is going to be passing back to normalizations, and then it's going to be normalized back and passing through the next block. Next, before we go into delve into more the Mamba architectures, we need to passing a little bit about the control theory. So the SSM, which is state space model, is the stable and structures equations, which is calculating for stable movement of the system. So we can use it in a lot of applications in real life in mechanism. And SSM have the two equations, which mean the state equations here, and this one is the output equations. And we have some argument. The first is uh, the first is HT or XT. This one is the hidden state considers the dynamic memories that keep track of the context. So what does is have to denote here is you the derivative, which mean is going to be represent the change over time here. And the YT is the output equations to calculate the output value. And in the control theory, we have some argument like A, B, C, D, and they are all the fixed argument. Next, we're gonna be moving to the model evolutions. So before Mamba, we have many structures or SSM-based model, and is S4. S4 is the structures SSM, one of the first deep learning structures, SSM, and it's used to fix argument like A, B, C, and delta, and it is not impacted by the XT input, and it's called S4 as the linear time invariant. So what is linear time? So like what I mentioned before, the SSM is linear time. That means that it's going to be scaling not in quadratic, but in just O of L or O of 1. And invariant mean because it's not changing over time. For example, like the first step is not going to be affected by or is going to be not impacted on the equations. So because the XT input is not impacted to the model, so that means like the input will not affected by XD. So that means like it's called invariant. and it is one of the biggest disadvantages that S6 aims to solve. And the next one is S5, the refinements of S4, and it's using the parallel scan in order to run this algorithm for SSM, and it's used fast Fourier transform. And S6 is the selective SSM, which is the extend SSM with the input independent parameters that use the selective mechanism and the hardware aware mechanism. And this architectures and this idea is used to generate and propose for the Mamba models, and it's called a linear time variant. So variant means the XD from each part will be impact to the models. So here's the fun fact. The model is built on S6. So basically we have six time of S letters, and it's called, and we can hear like the sound of the snakes like s. And the next one is because S6 is fast, so it's use a name Mamba. Mamba is one of the name of the snack. Here is the selective mechanism. So on the left side is going to be the math equations. So we have the derivative here, which I mentioned before is using to denote it's going to be changed over time. And on the right side, this is the equations that we'll use in the GPUs. So I will mention again, the HT or the HT with the derivative, that means that it's going to be used for state update value. You can see here. And we're going to be have the x with t minus 1 is equal to the xt here. This is the state before it. So we can understand like this. The second step will be depending on the step in the first step. So that is why we have the xt minus 1 and xt is going to be update to the time. And yt is the output. And the A, B, C is the tensors of matrix, and H is usually fixes for the stability of the models. Meanwhile, and then we're gonna have the question, where is the selective mechanism came from? And the mechanism, selective mechanism, will be come from the delta, which is here. Is it the core selective mechanism? And we will use it to discretize the state equations, and it will control the balance between how much we're going to be focused or ignore the current input. So we can see on the right side here, the 8 with the note here and the B here is going to be passed into the GPU. But because the GPU cannot itself calculate the derivative directly, it needs to discretize. Is discretized by what? Is going to be using this delta to discretize the A and B metric. Then it's going to be calculated. So here is the discretized rule. Like what I mentioned before, the GPU cannot directly calculate the derivative. So it's going to be discretized the A and B into the smaller part that GPU can calculate it. So we can look at here. This is the discretized rule, and I take it from the original papers, Mamba, uh, which is proposed by Jidao and Albert Gu. So here is the delta. So the delta, we're gonna be depending on the xt input, and the xt input will be used to calculate the delta, and the delta is then used to discretize for the A and B matrix. That's why it's called selective. The input will be depend and affect a lot to the A and B. So that's why it's called the selective one. Now let's move to the next part, is hardware-aware selective parallel scan. So before we understand it, we need to have the visualization, the basic component of GPUs. So the GPU will have the high bandwidth memories, so which is we can consider is at the VRAM. And inside of it is going to be have the GPU die, which is the processors, and it's have the L2 cache and the L1. the inside the GPU die is going to be really fast in calculations. And the ideas of the hardware selective parallel scan is like this. So in the long context task, we have the parameters like A, B, and delta is going to be have the complexity in calculations for O of B, L, D, N, which represent for B is the base size, L is the length, D is the dimension, and N is the state dimension. However, we have the problem. The more we're going to be processed like this, the complexities is going to be increased. If we just only calculate it at the HBM, the GPU cannot really process it well and fast. Although high bandwidth memories is the VRAM, it cannot process that fast. So we need to reduce one of these complexities at somewhere. So that is hardware where it came from. The complexity of it is just only BLD, and the N is the state dimension. It's just used solely to calculate for the selective mechanism inside SRAM. So here we have the main paradigm for the selective parallel scan, which is from the original Mamba papers. So at first we have the input here. We can see the green line is inside the HBM. Meanwhile, the orange one is calculated inside the SRAM. So the idea is basically is going to be calculated the N, which is the state dimension, inside of the SRAM. And the output is going to be calculated the output only. We can see the equation here. So I will explain a little bit. At first, it's going to be XD here is going to be using for selective mechanism to provide the delta. And the delta is used to discretize the B and A. This process is still in high bandwidth memory. After this, they are passed into the SRAM. The SRAM right now is going to be occupied for N, which is the state dimension. So the green one basically right now it just have the OBLN complexity. It just have only this. And when it's calculated inside of it, it's going to be having this state dimensions. So it's going to be reduced the state dimension of the models. And after this, when it's finished, the calculation of selective is going to be passing into the CT here, which is used to calculate the output. And we can see the green line here is calculated in HBM. So basically, the idea is going to be reduce the complexity and calculate it directly into the SRAM. Meanwhile, the output will calculate it in the high bandwidth memories. So what is the parallel scan we're asking previously? So the parallel scan is we passing through step by step, and here I use the visualization for recurrent scan, which means it's going to be passing in the hidden state 1, hidden state 2, respectively until the end. Is have the complexity of O of L. Meanwhile, the parallel scan is O of log L. We can see it's here. And note that the parallel scan will be completely different from the complexity of selective mechanism and all this thing like we mentioned before, or O of L or O of 1, because this parallel scan is the algorithm that we run on the GPU. So this is the complexity of it on the GPU, okay? So now we move to the strength and limitations. So Mamba is have the profound shift from sequence modeling efficiency and is have the overall in computations time and the storing state memory over 1. Because it's O of 1, basically like the hidden state of step 1 will be depending on the step 2. So it's going to be compressed next step. So it's going to be O of 1 and faster than the transformers. However, Mamba still have two largest weaknesses. The first is in the original papers, is still used for state dimension for n of 16. And this is the fixed sign that eventually forgot or overwrite the crucial extract detail of the high complexity task. So basically, like uh, the more we're gonna be compressed, it's gonna be forget because of this state dimension is quite small. It might be forget. So this is the first weakness. And the second one is parallel scan is not really optimized for GPUs. So most recent GPU, they use the CUDA core and is support for the operator, which mean like MATMU, the metric multiplications, which is more faster than this one. This one is still all log of L. The original Mamba, although it's fast, but it's not really utilize the optimize of GPU. So this and is quite hard to implement. So this is one of the disadvantages of Mamba. That is the next version gonna be improved. And here's is the parallel scan limitation visualization on GPU. So the original one is gonna be using the parallel scan like this. Previously, we can see is of log L, but in MATMU, it just only used for only one step in order to calculate it. And the current Mamba models, which is the Mamba version 1, is not utilized than Smart Move. So I do believe that in the next version is going to be solving this. So here is the empirical experiment on LLM. So on the original papers, Mamba is which is just only 1.4 billion parameters, but the average accuracy is even higher than double it twice for 2.7 billion parameters from the GPT or the hybrid one. And the more we can see here is even for Mamba 2.8 billion parameters, the accuracy of it is higher than even 6 billion or 6.7 billion. And the next one is going to be using for the DNA fold analysis task. So it's used for HT38 dataset, which is a DNA fold dataset, and it consists for 3.1 billion, the base pair token for ADN and ARM. And we can see here the Mamba is having more better performance. We can see here's the perplexities and the parameters in scaling. And the next is the speed in generations. So in the generation task, we can see here, for example, on the right side, I will took it. The Mamba is only 1.4 billion parameters. It's extremely faster. If we increase the batch size, we can see even for transformers 6.7 or transformer 1.3 billion, we can see over time it's always lowers and it's even out of memories if the batch size is increased. And the next one, we can see on the right side, the empirical test is on 8100 GPU, and we can see here the flat attention is really high, right? And we can also see like the convolution is the orange one. The scan is in the PyTorch, and the actual scan is from the Mamba in the red side here. The more the sequence length is increased, we can see the time is getting more faster, even though the flat attention is really support a lot here. So that is the end of my first video about explanations about the Mamba algorithm. And see you next time for the next video. Thank you for watching.